Okay, polynomial. Wait, there we go. Polynomial functions. I don't know why there's a thing for your name on it. The treasurer of the drama club determined the revenue R that the club can expect to generate for its next show as a function of the ticket price. So if you charge $0 for the ticket, you're not going to get any revenue. If you charge $1, then they expect this much revenue, $2, and so on, right? And if they charge like $8, they figured nobody's going to come. You know, we're not going to sell any tickets here. And so somewhere in this, and this, any retailer has to go through this, right? What do I charge for anybody, you know, offering a service with that? How much do I charge for my product or my service? If I charge too little, then I won't take in as much money as I might be able to. If I charge too much, then I won't be able to take in as much money as I might want to. So what's the sweet spot? Where is it? So what we're going to do is we're going to start by plotting the above data on your graphing calculator. So let's get out graphing calculators. And what we're going to do, turn it on, and I'm just going to clear out. So if you have anything in y equals, just go clear it out. And go second plus, and go to number 4. So second, and then plus sign, and number 4, which is clear all lists, and then hit enter. What that's going to do is it's going to clear out your lists, right? Any data that's sitting in the tables in your calculator will now be cleared out, right? So we're starting fresh. We're going to go to Stat, and we're going to hit Enter on Edit, and we want to be in L1. And in L1, we're going to put in the ticket price, right? Which is 0, 1, 2. So 0, 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to arrow over to L2, and we're going to put in the revenue. So the revenue for 0 is 0. And then we've got 350, 600, 750, 800, 750, 600, 350, and 0. And we're going to graph that. So if I just hit graph, I don't really see anything, right? Because this is just whatever window was left over from whatever I did before. And we can say, well, wait a second. Okay, look, your ticket prices go from 0 to 8. So let's set our x's to go maybe from 0 to 10. And the x scale can be 1. Right? It's a reasonable scale. And y min, well, we know that our minimum revenue is 0, and our maximum revenue is 800. So what do we want to put for a max? Yeah, sure, 1,000. Let's go with 1,000. And what's a good scale for that? Maybe 100. And now let's hit graph. Still, I don't see anything. So what we need to do is we need to go into, you go second y equal, go into your stat plots, and turn the plot on. And say, basically, what you're saying is, I want you to show me the data that I just put into the table. Okay, and there it is. So each of these guys here is one of the data points. And you can kind of see one down here, and you can kind of see one down here. So those are our data points. And that particular set of points is called a scatter plot. Okay, so let's just go in here, move this over. So that's called a scatter plot, which is just basically the raw data that you entered into your calculator, right? It's just like me giving you that and saying, here's a grid, plot the points, right? And you go in and just plot the points. So that's what we're doing on the calculator, is plotting the points. State the window settings for your graph. Okay, so what do we say? Our x's were 0 to 10 by 1, and our y's, we went 0 to 1,000 by 100. And what kind of shape is that? What kind of graph that you know? What does that look like? Is it linear, straight line? Quadratic? Yeah, parabola, right? So it's a quadratic. Okay. So looking at the shape of the data, we say, hey, this is a quadratic, right? So let's write that in. And what we're going to do then is we are going to run a quadratic regression on this. Or no, are we? Wait a sec. Now, determine a possible equation for this. Well, we could run a regression. So why don't we do a couple of things? Let's run a regression. So we'll go to Stat and over to Calc. And we'll go to number 5, which is Quad Reg. And we can hit Enter. And then we can hit Enter again. And it'll give us a quadratic in the form y equals, so quadratic regression on the calculator gave us, where's my calculator, y equals, now don't write out this, write it out as the actual equation, right? Y equals negative 50x squared plus 400x. Y equals negative 50x squared plus 400x. Okay, so that's one way for us to do an equation, right, is to let the calculator run a regression for us. But we've got other ways. Let's go back to the graph. So where's the vertex of this graph? Well, vertex is right here, right? And what's that point? So vertex. What's the vertex? You can read it out of the table. I guess I think I can trace the points. I can trace points. So the vertex is at 4 and 800, right? 4 and 800. And so we know that quadratic, so vertex form is y equals a x minus p squared plus q. Right? That's vertex form of a quadratic. And in this case, we have the p and the q because we have the vertex. Right? And so what we're going to do is just plug that in and then calculate the value of a. So we're going to say, and what we're going to do is we're going to change our values a little bit, right? Because it's a revenue function, it's using R, and the dollars that we're using are the ticket price, which is T. So we're going to use a variable. Instead of Y, we're going to use R. Instead of X, we're going to use T. Okay, so over here, we would write R equals negative 50t squared plus 400t. And over here, we're going to write R equals A. Okay, we still don't know A, right? But we do know P and Q. Okay, we're using T for X, so it's going to be T minus 4 squared plus 800. Right, and now what we're going to do is we're going to plug in one point that we know, right? Any point. So we could plug in the point 0, 0, right? If you have 0 revenue, you're going to get $0. We could plug in the point 1, 350, or 2, 600, or 3, 750. We cannot plug in the point 4, 800, right? But we can plug in any other point. So any preferences? What do you like? 0, 1, 350? Okay. So we're going to plug in the point 1 and 350. So we say we get a revenue of $350 when the ticket price is 1. And so a little bit of algebra later. Clear a little space here. So 350 is equal to, I don't know, how much detail do you want? 1 minus 4 is 3. 3 squared is 9, right? So we're going to get 9a plus 800. Subtract 800 from both sides. What's 350 minus 800? Negative 450. And so A is equal to negative 50. And our equation is going to be revenue is equal to negative 50 t minus 4 squared plus 800. Well, either of these two. These are actually both the same, right? If I expanded this, multiplied everything by -50 and added the 800, I would end up with this. So one is using our knowledge of quadratics, right? We know what vertex form looks like, so that's an algebraic solution. If I asked you to solve algebraically, the one on the left, right? You're going to say, okay, here's my vertex, here's the vertex form, I'm plugging in, I'm putting in a point that's on there, and I'm solving for A, and there's my answer. If I say, run the regression equation, you can run the regression, here's my answer. Okay? And they are both the same, right? I mean, they'll work. If we, well, here, we'll do it off here. So -50 t minus 4 squared plus 800. Okay, so this will be t squared minus 8t plus 16 plus 800. Right, we're going to multiply. So we get -50t squared plus 400t minus 800 plus 800. Or -50t squared plus 400t. Okay, so they're identical equations, right? Now, the thing is, if you're using real-world data, it's usually not as perfect, right? I mean, in this case it is, but if we're doing measurements or something which look quadratic, then these may in fact be different, right? Because you're basically picking a model, and models aren't necessarily perfect with the world. Okay, any questions on A? Okay, so we plot the points, we draw a scatter plot, we show it in our graph using an appropriate window, etc. Part B, the base cost to produce the show is $650, right? Remember, revenue is just how much money we're going to take in. Profit is revenue minus cost, right? If you want to know how much money you're going to make, well, how much did I take in, how much did it cost me? So if you're selling a product, you know, it's not just, hey, I'm going to take in $1,000. Yeah, but your product cost you $1,100. You're losing $100, right? So, okay, I need more revenue. Base cost to produce the show is $650. However, increasing the quality of the show will increase the cost to stage it. To cover the higher cost, the drama club can increase the ticket price. For each $1 increase in the ticket price, the club can spend $25 more on producing the show. Make a table of values to show the relationship between the cost of the show C and the ticket price T. So if we just go with the base ticket price, how much does it cost to produce the show? $650, right? $650. If we raise the price by $1, then how much can we spend on the show? $6.75. $2? $3? $4? $5? $6? $7? $8? Plot the above data on the same graph. Okay, I need to calculate. Let me turn this back on. So we're going to go to Stat. We're going to go to Edit. We're going to go to L3. Okay, so here we're going to enter. So if so L1 is ticket price, L2 is revenue, L3 is cost. Okay, so we're going to put in 650, 675, 700, 725, 800, 850. Now, if I want to graph this, right? If I just hit graph, we're just going to see our original graph. So we're going to go to y equals, or sorry, second y equals. Go to stat plot, and what we're going to do is we're going to turn on plot 2. So plot 1 is our revenue, right? Ticket price on the x, revenue. Plot 2, we're going to say, okay, so same thing. I'm going to turn this on. This is the scatter plot, right? Just plot the points. My x list is L1, right? That's still the ticket price. My y list this time, though, is L3. So to get L3, we go second function 3. You see the little yellow L3 here? So you go second 3, and it'll put an L3 in there. Okay, so my y values are now going to come from L3. Now we hit graph, and we can see the two sets of data, right? So this was our original, which is revenue, and this is cost. Okay. So we have revenue and we have cost. The cost function, what kind of graph is this? Linear, right? Straight line. So what type of function? Linear, quadratic? It's linear. Determine a possible equation for the cost function. Okay, again, we could do this a couple of ways. We can run a linear regression, or we can work with algebra. So let's do the algebra first this time. So since it's a linear equations look like this, right? Y equals mx plus b. We're not using x and y though. We're using c for cost and t. So we're going to write c is equal to mt plus b. M is the slope and b is the y-intercept. Okay, we know the y-intercept, right? Because when x is 0, that's when you get your y-intercept. So that's 650. And the slope is actually 25, right? Because every time we go up by 1, we go up by 25. Okay, so the cost function is 25t plus 650. Okay, and you can get slope either, you can run it by taking 2 points and going y2, like 750 minus 650 over 4 minus 0 is 100 over 4 is 25, right? Since the line has a constant slope, it doesn't matter which points you pick to work it out. We can, using the calculator, you go stat, calc, linear regression. But now you've got to tell it that it's in L1 and then comma and L3. So you say, I want you to run a linear regression. My x values are in list 1, but my y values are in list 3. If you just run regression and don't say anything, it'll always use L1 and L2. That's what it defaults to. So when I ran that quad reg, I just said quad reg and hit enter. And it's going to say, okay, x's are in L1, y's are in L2. And we get 25x plus 650, right? Okay, so either way, right? Using a regression from the calculator or using algebra, an algebraic expression. Now, I don't think we actually do anything with the thing from this point on, right? But I mean, what you might want to do then is to analyze these and just sort of say, well, I would like my revenue to be greater than my cost, so there's no point in being down here. We want to be somewhere here where revenue exceeds cost, right? And that's how we'll decide what ticket price to charge. All right, polynomial function definition. Function that contains only the operations of multiplication and addition or subtraction with real number coefficients. Okay, real numbers can include radicals, right? Can include decimals, integers, whatever. Whole number exponents. So your exponents have to be 0, 1, 2, 3, 4, 5, 6, all right? They have to be whole numbers. And 2 variables. Usually we use x and y, right? But in this case we were using r and c or r and t. The degree of the function is the greatest exponent of the function. Okay, so you look for the biggest exponent, that becomes the degree. The degree of a polynomial function determines the shape of the graph of the function. Okay, we're going to complete the table on the next page and summarize the properties of different polynomial functions. So the first type of function we're looking at is of degree 0, and it's called a constant function. I might want to, I don't know if I want to shrink this down a bit so the whole thing fits on the, let's see if we can view, give a certain percent. That's not so bad. I mean, yeah, the whole thing kind of fits on there now. So we've got a constant function. So constant function looks like, well, like this, right? So this is a constant function. This would be y equals 3. And I'm just going to go into decimals, which I don't have one of. Let's just go into. This will just make for nicer graphs. And we're going to type in y equals 3. Okay, so there we go. There's a constant function. It's a horizontal line. We want to get various characteristics of it. So how many x-intercepts are there? for this particular? None. Okay, so 0. How many y-intercepts are there? 1. There it is right there, right? But touch it. No, that's pretty. Never mind. What is the end behavior? So by end behavior, we're saying, you know, we know this graph keeps going, right? There's like arrows on both ends. All of these graphs have arrows on both ends, right? And so by saying the end behavior, we're saying, well, okay, where is it going? And we're going to do that by saying left to right, okay? Because that's how we read, so that's what we're going to do. So as the graph goes from left to right, it goes from quadrant 2 to quadrant 1, okay? Which means we should maybe step back and name the quadrants for a second. So let's go back here. This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. Okay? So quadrant 1 is the upper right. And then we go counterclockwise. Okay? So we go 1, 2, 3, 4. So we talk about the end behavior, we're talking about, okay, what does it do? It goes from quadrant 2 to quadrant 1. Okay, wait a sec. So x-intercepts, we said there were none. Y-intercepts, there was 1. End behavior goes quadrant 2 to quadrant 1. But what does this one do? This one down here, y equals negative 2. Let's go back here. We'll add that in. Okay. Y equals negative 2. Okay, here's another graph. How many x-intercepts? None. Y-intercepts? 1. End behavior? Quadrant 3 to quadrant 4. Okay. But I can give you one more. Here's one just to throw a little wrench in here. What if I graph this? So the orange line here, y equals 0. How many x-intercepts? A lot. Yeah, infinitely many, right? That's all it is. It is the x-axis. So usually there's none, right? Because it's a horizontal line, so it runs parallel to the axis, so it won't go through the x-axis. But if it's y equals 0, then there are infinitely many x-intercepts. So that's also a possibility that we have to keep in mind as we go back to this. Okay, so quadrant 2 to quadrant 1, or quadrant 3 to quadrant 4. Number of x-intercepts, 0, unless it is y equals 0.
I'm new too.
You're new. Let me get you some stuff. One of these, that's what we're on now. One of these, that's what we did, and I'll get you some other stuff later. Domain. What is the domain of this constant function, y equals 5 or whatever? Are there any x values you can't put in? It's actually, in a sense, it's kind of a weird function, right? Because the equation would be something like y equals 3, and I'm asking you about x values. Okay? X is 7, what's y? 3. X is 2, what's y? 3. X is negative 5, what's y? 3. X is anything, what's y? 3. So the domain is x belongs to the reals, even though there isn't actually an x in the equation. The range. It's a set of all y's such that y is a constant. So okay, there's a value for y, whatever it is, but that's it, right? There is only one value for y. Could be 3, could be 2, could be 0, could be anything. Number of turning points. Does this graph turn? No, it's right, it's a straight line. It's like driving through Saskatchewan. You do not turn. Okay, number of turning points, 0, right, or none. And that is the constant function. Okay, linear function. A linear function is of degree 1. It has x to the power of 1, right? So let's see. Can I hide them all? I don't know. Okay, how do I unhide? Ah, there we go. Okay, y equals, pick a number, any number. 4. There's y equals 4x. Pick another number, any other number. Minus 6. Okay, this is the graph y equals 4x minus 6. Okay, it is a linear function. Let's run through all the characteristics, right? So what do we got? How many x-intercepts are there? Where's the other one? Okay, so 1 x-intercept. How many y-intercepts? 1. Okay. End behavior. Where does this start? Which we can't exactly see there. So where does this start? Which quadrant? 3. And it goes to quadrant 1, right? So quadrant 3 to quadrant 1. Do all linear functions do that? Can I make a linear function that doesn't go quadrant 3 to quadrant 1? What would I do? How about y equals what? Negative 4 x. And do anything with that? Minus 2, let's say. How many x-intercepts for the black one? 1. How many y-intercepts? 1. There's no change, right? Linear. So can you imagine any linear that won't have 1 x and 1 y-intercept? Other than a horizontal line, right? Which is actually a constant function. And there is one other one, right? There's a vertical line. Okay, if we did that, but that's not what we're looking at, right? We want a polynomial function. We really want to have those variables. Okay, so 1x, 1y, and the end behavior is either quadrant 3 to quadrant 1 or what's this one? Yeah, quadrant 4 to quadrant 2, right? So let's go back here. So remember our quadrants, right? So we're either going this way, up to the right. So sometimes I'll describe end behavior as like up to the right, okay? Or down, up. In this case, it's kind of flat. So end behavior, you say, well, it's flat. This is down, up, right? It starts down, goes up. This is up, down, right? Going up, and then it's going down. So as I say those, I'm saying them, this is what it's doing on the left, this is what it's doing on the right. So this one is down, up. Down to the left, up to the right. This one is up, down, okay? Or, you know, I guess maybe describing it by saying which quadrants makes it a little more obvious, right? Okay, what do we say? X-intercepts, there was 1. Y-intercepts, there was 1. This was quadrant 3 to quadrant 1. Or quadrant 4 to quadrant 2. Domain. Any x's you can't put in? No. Range? Because we're going like this. What y values are we covering? Or what y values aren't we covering? You got all of them, right? All real numbers. Okay, so set of all y such that y belongs to the reals. Right, with the constant function, it's a constant, right? You only get that one number. But with the linear function, it's all real numbers, right? Turning points, does it turn anywhere? No. So 0 or none. Okay, 2 more. Quadratics. Quadratics are of degree 2. Let's go do some quadratics. So there's some that are given there for you, right? We can do some others. hang on, let's drag this back into the middle. Okay, give me a quadratic. What would you like? 2x squared. Anything else? Minus 4x plus 2. Okay. How many x-intercepts does that have? 1. What if, okay, here, let's enter the same thing down here. So we'll go 2x squared equals 2x squared minus 4x minus 2. How many x-intercepts does that have? 2. So we could have 1, we could have 2, or we could have what? 2x squared minus 4x plus 2. Oops. Plus 3. So, how many x-intercepts? None. So you can have no x-intercepts, 1 x-intercept, or 2. Any other possibility? No. Okay? But we could do this. Okay, so there's another one, right? This has 2 x-intercepts and that. But when we come to discuss end behavior, we're going to look at, well, okay, it could be this or it could be that, right? We know that it can open up or it can open down. Okay, so let's see if we can go summarize that. All right, so number of x-intercepts. What are we going to say? So 0, 1, or 2. You have no x-intercepts, you can have 1 x-intercept, you can have 2. How many y-intercepts? 1, right? There's only 1. Each of these guys can only cross the y-axis once. End behavior. Well, it starts here, ends here. So it goes from quadrant 2 to quadrant, so quadrant 2 to quadrant 1, or it opens down and it goes quadrant, okay, remember going from left to right, quadrant 3 to quadrant 4, or Q3 to Q4, right? Just relabel the quadrants here. Whoops. Okay, 1, 2, 3, 4. So it goes quadrant 2 to quadrant 1, or we could describe that as up, up, right? This, the left end goes up, the right end goes up. Or down, down. The left end goes down, the right end goes down. What else we got? Domain. What's the domain for this? Let me give you a hint. All polynomial functions have the same domain. So the domain is x belongs to the reals. What's the range? Okay, so it depends, right? And here's how we're going to say it. It's either the set of all y such that y is greater than or equal to the minimum, or y is less than or equal to the maximum. Okay? So if it opens down, it has a maximum, and all the y values are less than or equal to that max. If it opens up, it has a minimum, and all the y values are greater than or equal to that minimum. Turning points. If you're driving along the curve, do you have to turn? How many turning points? There is always one. Okay, always one turning point. Okay, because at some point as you drive along that curve, you have to turn so that you can go.
Oh, are we talking about all three graphs?
Well, any quadratic. We're talking about any quadratic. Or every quadratic. Every quadratic has one turning point, right? Because it has to go, like it's going down and now it's going up. Or it's going up and now it's going down. So there's a turning point there. Cubix. So here are some examples of cubics. Let's go do some of our own. So a cubic is going to be of degree 3. It's going to have an x cubed. So the simplest cubic, I'll get rid of these. There we go. The simplest cubic is y equals x cubed. But we can change things here, right? So give me something else. What else would you like? How about an x squared? So let's go plus, pick a number. 4x squared. Now you can notice what happens there, right? Maybe we need to zoom out a bit. Okay. So we can see, oh, so it takes on that kind of shape. Let's keep going. What else could we do? We could do more to this, right? So 4x squared, plus or minus? Minus? Pick a number. 5. Minus 5x. That changed it again a little bit, right? But so its shape is changing a bit. How many x-intercepts do we have? There are 3. Okay. What if, let's go back here. Let's say I move this graph up 4. How many x-intercepts? 1. Let's go back to the original. How many x-intercepts? 1. Are you always going to have at least 1 x-intercept? Okay. Could we have 2 x-intercepts? Could we have 3? Well, we've seen 3. So we could have how many x-intercepts? 1, 2, or 3. What happens if we flip this around, right? Because we've seen that stuff happens when I put a minus sign in here. So there's a minus sign. That changed the x-intercept? No, but it did change. What did it change? What characteristic? So I'll just kind of flip it back and forth. So what's changing? Oops. Of the things that we've been looking at, what am I changing by doing this? The end behavior, right? Okay, and then that won't matter. Let's go back and let's throw this in. So we get plus 4x squared. Okay, look, so now I've got 2 x-intercepts, right? And let's go back here. So now what am I changing? So what changes the end behavior? Yeah, making the leading coefficient negative, right? That changed our parabola from opening up to opening down. Changes our cubic from, well, let's go describe this stuff. Okay, based on what we've seen. Number of x-intercepts. 1, 2, or 3, okay? You can't have 0. Number of y-intercepts. 1. Looking at the number of y-intercepts for all of these, what conclusion might you make about polynomial functions? They only have 1 y-intercept. You think that's true? How do you get the y-intercept? Set x to 0. So if you think about polynomial function, right, even if it was like x to the 6th, and then something x to the 5th, and x to the 4th, and cubed, and squared, and x, how do you get the y-intercept? You're just looking at the constant number, right? That's your y-intercept. Because everything with an x in it is going to disappear. So you will only ever have, and you will always have, 1 y-intercept, right? And it's just the number that's at the end. It's the constant term. End behavior. So what's it doing? Let's take this one. Or let's take this one. Wow. Let's go back here. Let's get rid of that negative. So let's do a positive end. Positive end behavior is from where to where? Where does it start? Quadrant 3 to quadrant 1. Now, if I was describing in words, I might say down up, right? Comes from down and it ends up going up. But we're using quadrant 3 to quadrant 1. Or what happens when we do put that negative in? Quadrant 2 to quadrant 4, right? So remember, that's saying something, right? Because quadrant 4 to 2 is different than 2 to 4, right? Quadrant 2 to 4 says you're starting out going up and you're ending up going down, right? You're starting in an upper quadrant, you're going to a down quadrant. All right, or quadrant 2, quadrant 4. Domain. Same as everything else, right? Range. Range. It's already written somewhere on the page, the range. Is it the same as quadratic or the same as linear? Range. Really? Let me take this line and sort of stretch it. It's going to look like a straight line, right? So it goes up to down, right? What's your end behavior? Check your end behavior based on this end behavior. 3 to 1 or 4 to 2, right? So in other words, it's going opposite quadrants. Whereas this one is, for quadratic, it's 2 to 1, right? Both up. This is 1 up, 1 down. So it's a set of all y. Right. It has to cover everything off because it's always going from down to up or from up to down. Okay? And if you're going down to up or up to down, you're covering all the y values. Right? If you're going up, up or down, down, you're not covering all the y values. Turning points. There can be 2 or there could be 0. Okay? And just to show you the 0, let's go back to here. Okay, so they're calling this, there are no turning points. This is called a point of inflection. I like to think of it as a turning point, but I guess it's not. So we're going to call it not a turning point. Okay, so there are none or there are 2, right? Because you're going to get the peaks. All right, and that's that for that.